Now to continue with the RC high frequency response of amplifier, we continue with the slides. So this is now by Miller's theorem, this is the simplified circuit of which is known as equivalent high frequency circuit, we can call it. Okay, further, okay, so we have two capacitors in the input, okay, C in Miller and CBE, okay, and then another capacitor C out, and the load and the collector resistor. Now let's suppose we want to study the the high frequency response at the input. So in that case, at the input, I can ignore this part. Okay, the only part I would take is the input side, or the part where we can assume something at the base. So basically, when I take this part into consideration, okay, so it means that I can further simplify the circuit as shown over here. Remember, okay, I can take into account R1 and R2, CBE, C in mil, okay, and I can replace this by its R in base, this amplifier by this equivalent resistance, which is R in base, given by beta AC RE, and I ignore this part. Okay, so now further I can combine these two resistors, because these two resistors are in parallel, so I can take it out like this. Okay, and I can combine these two capacitors. So remember, capacitors, when they are in parallel, they can be added. So this is the value, we can add them up. Okay, so now the equivalent, this is further simplified by to this circuit. So if you see, this is an equivalent RC circuit, okay, at the input. Remember, at the input. Okay, we are not talking about output, because the same for the output we have to repeat the same analysis. Okay, so we are not going to take this for the time being. We are only concerned with the input. So this is the equivalent RC circuit at the input. Okay, and this are equivalent high frequency input RC circuit. So you have R and you have C. Now C is given by this formula, this combination of CBE and C in mil, and R, the equivalent resistance, is given by this. Now a critical frequency, if it occurs, okay, for a critical frequency, the condition is that this R would be equal to XC. Okay, this, so I can make equal this R to XC over here. So this is XC, when they are equal, this XC, and this is R. Okay, when I can calculate the, okay, in that case, the critical frequency, which is given by this, and the phase shift, which is given by tan inverse, now R divided by S XC. Now remember, this one is different from the low frequency phase shift, okay, because the RC over here is different from the lower frequency. Over here, this is a low pass RC circuit. Remember, this is low pass RC circuit, right? Okay, and in the previous, for the for low frequency, it was a high pass RC circuit. Anyhow, this is the critical frequency equation, this is the phase shift. Now if you can see the value, if I graph it, okay, if I plot a graph between the frequency and the voltage gain, okay, so this is different from the previous one. Okay, now when frequency, okay, when frequency is increased, okay, so definitely the voltage gain, there will be reduction in the voltage gain for critical frequency. Then if you by further increase in the decade, so a further voltage drop in the gain, and similarly the same process can be repeated. Now what we do over here, now this is example 10.11. we can finish this as okay. It says that derive the equivalent high frequency input circuit for a BJT amplifier in figure. This figure is given, okay, derive the equivalent high frequency input circuit. So high frequency input circuit is given by this RC, okay. So you first you construct the RC circuit, but we don't know about this R value and this C value, so we need to find out, okay. And also determine the upper critical frequency due to the input circuit. The transistor gives you this, and so all the data is given. So first of all we construct this RC circuit. Now we want to evaluate, compute the value of R and this C, right. So R is a combination of R1 parallel to R2 parallel to R in base, right. So you put the value 600 for 4.7 22, okay. And then okay, because there is also RS, so this will also come into play. The input source resistance 600, okay. And this is beta AC, this is beta AC, very simple, okay. This is 11.1 is basically your RE, and this is unfortunately we don't know. So if we don't know about this RE prime, this is this RE prime, so for that we have to apply our previous knowledge, and this is the procedure where you calculate your RE prime. So your RE prime comes out to be 11.1 ohms, right. So when this is done, so you put the values, so the effective resistance comes out to be 378, okay. So the value of this is 378, okay. The only thing in this part was to unknown was to calculate RE prime, and you know what is the procedure to calculate it. Now for the C in mil for capacitor CBE, the first part is CBE. CB is given 20 farad. C in Miller is basically over here by formula. This is you can, the gain is okay, but the gain also the gain, but unfortunately again the gain is not known, but CBC is known, 1 is your constant. So for the gain of this is a common emitter amplifier, and we know that for a common emitter amplifier the value of the gain is given by this equation, this from our previous knowledge. So gain comes out to be 99. So 99 plus 1 is 100 times CBC is 2.4. So this is the capacitance value, right. So the total capacitance value, you add this one plus with this one, right. So 260 picofarad will be 260 picofarad. This is the value is 260 picofarad, right. Now this is done. Now determine the critical frequency. Due to the critical frequency, the formula is given by this equation. So R in total is 378, R C in total is 260. You put the value, and this comes out to be 1.62. So this is all about the high frequency response of amplifier. Thank you.